Consider this function f of x equals to x cubed. Now, if we take its derivative, we know it yields 3x squared via the power rule. But what if we flip the question such that it asks, what function, when derived, yields 3x squared? Well, you might think it's easy to answer, given the original function we started with, x cubed. But what if we weren't given that information and had a more complex function, like so? If you were to guess the original function by imagining it, I suppose it would be extremely difficult. In fact, the actual f of x we're looking for is this. Pretty complex, isn't it? To visualize what we did, we need to bridge the relationship between f of x and its derivative f prime of x. To get f prime of x, given that we are starting from f of x, we would need to use the process called differentiation. Likewise, if we were to get f of x, given that we are starting from f prime of x, we would need to reverse the whole process called anti-differentiation. And oh yeah, why is there a plus c? Let's go back to the earlier function to make it simpler to visualize.
Notice that f of x equals x cubed is not the only solution. Well then, what are the other possible solutions? If you notice, if we add constants, that is, any numbers or variables independent of x, we still get the same derivative, 3x squared. We can go crazy with these constants or numbers. We can add more and more numbers, even extremely big numbers, and it will eventually yield the same derivative, due to the rule where the derivative of a constant will always equal 0. We would then rewrite this constant as c, so now we know for a fact that x cubed plus any constant c is the general solution. Formally, we would define it in this way. For any arbitrary constant c, the function f of x equals x cubed plus c is an antiderivative of f prime. The general representation of antiderivatives is as follows. If f is an antiderivative of f prime on an interval I, then g is an antiderivative of f on the interval I if and only if g is of the form g of x equals f of x plus c for all x in I where c is a constant. The family of functions represented by g is the general antiderivative of f, and g of x equals to f of x plus c is the general solution.
Moving on to notations, there are similarities between differentiation and anti-differentiation. While there are different notations for differentiation like dy over dx, y prime, and f prime of x, the most famous notation for anti-differentiation is the Leibniz notation. As such, the not-so-common Newton's notation, like the letter y with a vertical dash on top. But for ease, we should analyze Leibniz notation and what it essentially means. Traditionally, antiderivatives are called integration, and this spaghetti or worm-looking shape is widely known as the integral symbol. The function inside, f of x, is the integrand, and the x in dx represents the variable of integration. When we integrate the function f of x, it will yield another function capital F of x, which denotes the antiderivative of f of x plus c, which is an arbitrary constant of integration. Earlier, we mentioned the anti-differentiation or integration has a strong relationship with differentiation. Note that these operations are inversely correlated to each other. Hence, it will be feasible to show that the antiderivative of the derivative of capital F of x yields the same capital of f of x plus a constant, and the derivative of the antiderivative of f of x will ultimately yield in f of x itself. This is a crucial fact that we have obtained as we further determine the rules of integration or basic integration formulae by reversing the known differentiation formulae like such. The derivative of a constant c is equals to 0, therefore the antiderivative of 0 will return to c. The derivative of k times x will just yield in k, integrating k will return k times x plus c. Now this rule goes for algebraic functions shown here, and even transcendental functions like trigonometric and exponential functions.
The most important rule for integration is the power rule, or the inverse power rule. If we integrate x to the power of n dx, all we have to do is add 1 to the exponent, and then divide everything by that same exponent. Also, do not forget plus c. Put everything aside for now and keep the formula in a box. Let's say if we were to confirm this rule to be true, then let's test it out from the initial example. Let's integrate 3x squared and see if it results in x cubed. Move the 3 out as per constant multiple rule. Then integrate x squared by using the same technique. Add 1 to the exponent, then divide everything by that same new exponent. Don't forget plus c. Now, expand the parentheses, and we will get x cubed plus 3c. But as we know, c is just a constant, so what's the difference between c and 3c? Nothing. It remains a constant, and therefore we can write that as c. X cubed plus c is the answer. Okay, here's another interesting case. We are to find the antiderivative of the square root of x plus 5 dx. We would first rewrite the square root of x as x to the power of half plus 5 times x to the power of 0, as it is equivalent. We then split the integrand into two parts, separated by the plus sign. Now, we have the first part and the second part. The first part will use the power rule like the previous examples we did, and add c. However, to easily differentiate between the first and the second constant, we will write this as c1. The second part will also use the power rule like so. Then we write the constant as c2. We would then simplify and rearrange like terms up to here. Now, let's analyze c1 and c2. They are both constants, even though they come from different integrands. Hence, we can group these by letting c equal to c1 plus c2, thus leaving us with the solution.
One of the crucial applications of antiderivatives in real life is kinematic equations, which deals pretty much with position, velocity, and acceleration. The position function in terms of time, when derived, yields its slope, also known as velocity. Likewise, deriving the velocity function with respect to time will yield its acceleration. Remember that we can reverse this whole process of differentiation by anti-differentiation. This is useful as we can generate more formulas from the data provided and work more thoroughly to solve day-to-day problems. Let's assume that we are given the acceleration a is constant, and we are to find the formulas for velocity and position functions in terms of t, or time. To obtain velocity, we will simply integrate acceleration with respect to t, and obtain a times t plus c. However, c is just a constant, and since this is the function for velocity, we can replace c with v sub 0, or the initial velocity. Next, to find the position function, we would integrate velocity with respect to t. Remember that velocity is equal to this. By applying the power rule, we get x of t equals to 1/2 at squared plus v sub 0 t plus c. Again, c is just a constant, and we can replace it with the initial position, or x sub 0. So now we have the ultimate tools to solve daily kinematic problems. Let's take a sample problem and solve using the formula we obtained earlier.
At the instant the traffic light turns green, a car that has been waiting at an intersection starts with a constant acceleration of 6 feet per second. At the same instant, a truck traveling with a constant velocity of 30 feet per second passes the car. Now we are provided with two questions. how far beyond its starting point will the car passes the truck, and how fast will the car be traveling when it passes the truck. So we know that the car with an initial velocity of 0 is accelerating at 6 feet per second. That is, for every second, its velocity or speed increases by 6. The truck, on the other hand, has an initial and constant velocity of 30 feet per second, and it does not accelerate. Knowing this data, the truck is of course going to whiz past the car and leave it behind. But after a while, the car will catch up and overtake the truck. Question A asks us to figure out what that displacement is. Our strategy is to use the kinetic formula we've previously obtained, and in this particular problem, we use the position formula. Let's split the position formula into two parts, one for the car and one for the truck. For the car, as noted, the initial velocity is 0, so that's going to eliminate this term. For the truck, once again, it's traveling with a constant speed, so that means the acceleration is 0, and we can therefore knock out this term. So both equations simplify. From the animation, we can see that the displacements will be equal once the car reaches the truck and overtakes it. So we can set these two expressions for displacement equal to one another. We now have an equation that we can solve for time. To do that, we can divide both sides by 3 and move 10t to the other side. Factor it out, and we get t equal to 0 seconds and t equal to 10 seconds. Note that t equals to 0 is the initial time where nothing has happened, and that's not what we're trying to find. So we can eliminate that, and resulting t equals to 10 seconds. We're not done yet. We need to find the position or the displacement from the given time. So we can plug in 10 for time, and we obtain the displacement, which is 300 feet. So the car passes the truck 300 feet from the start.
Next, question B asks us, how fast will the car be traveling when it passes the truck? In other words, what is the velocity of the car at that instant? Well, to find velocity, we would apply the kinematic formula for velocity, which is v equals v sub 0 plus a times t. And we know for a fact that the car has no initial velocity, so we can cancel that out. Then, we would input t equals 10 to the equation, and we obtained that the car was traveling at 60 feet per second at that instant.
If you've understood everything up to this point, you now have a very strong foundation in what integration or anti-differentiation is all about. Do let us know if you have any questions. Thanks for watching.